Hello everyone. Today we're going to learn how to apply everything that we've been doing with transformations to the parent graph of the quadratic function. Now the parent function is basically the most simple form of that particular function. So without any stretches, without any translations or dilations or reflections or anything like that. Today we're going to focus particularly on the quadratic. The parent quadratic function is just f of x is equal to x squared. That is without anything. And this is the graph of the f of x is equal to x squared, which that means that while we do all of our transformations, all of our graphs are going to have some form of this U shape, which is called a parabola. Now the quadratic has a vertex, which is located at 0, 0. It is the point where your graph changes from decreasing to increasing. It's like the very center of that quadratic. Now, this is called a reference point. And your reference points are points that you can find on the original graph that's going to help us with our transformations. The vertex, which is 0, 0, is very important, and we use it often when we're doing our transformations, along with other points such as negative 1, 1 and 1, 1. You see how negative 1, 1 is located on the function, and so is 1, 1. So what we're going to do is we're going to figure out the transformations that are present on the graph, and then we're going to move these points, and when we move or stretch or whatever transformation we apply to these points, then we're able to plot those points and then just connect them to create that U shape. So first we're just going to practice on how to see what transformations are being applied. If we look at the equation, g of x is equal to negative 3 parentheses x minus 2 squared minus 4. So remember, the parent function is x squared. So everything that you see highlighted in a different color represents all of those different transformations. So if I go in order, remember that the negative, if it's on the outside of your function, in the case of the quadratic, you'll see that we have parentheses. Anything outside of the parentheses is going to affect your y values, and anything inside the parentheses affects your x values. Now, we don't do anything with the exponent right now. The exponent is just to let us know that our graph is going to look like the parabola. This is the function that we're graphing. So first, when we look at this equation, we see that we have this negative on the outside, meaning that it is a vertical reflection. And if it's flipping over vertically, that means it is reflecting along the x-axis. Now the 3 that is on the outside, it is being multiplied to the parentheses. Therefore, it is a vertical stretch. And it's a stretch because if you multiply anything by 3, it will get bigger. So that's a vertical stretch. The minus 2 inside the parentheses, remember when you're adding or subtracting, those are your translations. And anything inside the parentheses, you're going to do the opposite. So this will mean that the graph would move right 2 units. And our last transformation, we have this minus 4, meaning it will move down 4. So now, how do I translate these transformations onto a graph? Let's look at another example. We have parentheses 1/2 parentheses x plus 5 squared plus 2. Now, when we're figuring out our transformations, if we have double parentheses, you look at the outermost parentheses, and everything inside of that are your transformations that are affecting the x's. The dilations and reflections that occur to the x's are always written outside of a parentheses because that's to indicate that we are first doing the dilation and reflection, and then we'll follow that up with the translation. But anyway, we have this 1/2 on the inside, which means that you would take the x values and divide it by 2. But remember that since it's in the parentheses, we're actually doing the opposite. So instead of dividing the 2, you are multiplying by 2. So this will be a horizontal stretch of 2. Then this plus 5 That is your translation, meaning that it will move left 5. And finally, this plus 2 that is on the outside, that means that the graph is going to move up 2. So in order to apply these transformations to our graph, we have to write the transformation rule for the x's and the y's. Now, when we're writing our rules, we look at everything that is on the inside. And remember that it has to be the opposite. So just think about it as if you're reading from left to right. Instead of dividing 2, I will multiply 2. And what am I multiplying? I'm multiplying the x's. So think 2x, and instead of plus 5, we would write minus 5. Then think of this is x squared, right? Or rather, from the parent function, all of that is applied to your x's, and think of this as kind of like your y. So if you read it, again, from left to right, now trying to write the rule for the y's, it would be y plus 2. Once we have our transformation rule, we take our reference points that we determined from the previous slide, and these are the points we're always going to use. Now, I didn't mention this, but how this works is xy represents the points on our original function, which are these down here. The arrows are just meaning like, okay, so this is the xy that I have, and it is now going to be transformed into this. So I am coming up with the new coordinates. So what I do is I take the x value and I plug it in for the x rule. And then I take the y value and I plug it into the y rule. So if I plug in -1 into the x, I would have 2 times -1, which is -2, and then minus 5, so -7. Then I plug in the 1 into the rule for the y. So I do 1 plus 2, which is 3. Then I plug in 0, 0. So 0 for the x, 2 times 0 is 0, minus 5 is -5. When I plug in 0 for the y, 0 plus 2 is 2. And then finally, again, I plug in this last reference point. 1 for the x will give me 2 times 1, which is 2, and 2 minus 5 is -3. Then when I plug in 1 for the y, 1 plus 2 is 3. So these are my new points. This represents the points that are on my transformed function. So I'm going to go ahead and plot that. So we have -7, 3, -5, 2, and -3, 3. See how we have those 3 dots? This is already the general form, like the general shape of your parabola. So all you would have to do is connect it, and you're done. Make sure that it is a smooth curve. This is not a V. That would be a different graph. So now we're just going to practice with a few other examples. We're always going to start off the same way. We're going to write out the transformations. And the reason I do that is not only just so that we know what transformations are being applied, but additionally, if I know what these transformations are, and I look at my graph, it should reflect what those transformations are saying. So the horizontal stretch of 2, you can see that it was widened out. It is a wider parabola. Then it moved to the left 5. If the parabola originally starts at 0, 0 at the vertex, notice that now the vertex is at -5, meaning it moved to the left 5. Additionally, the vertex has a y value of 0, so we can see that it moved up 2, like we said it would. So if you applied your rules correctly, it should reflect what you said it was going to do. So in this example, we have a negative on the inside. Remember that anything that is in the outermost parentheses, that affects your x values. So what I'm going to do is I'm going to highlight this. This represents everything that is on the inside. And then this represents everything that is on the outside. And that can kind of give you a visual cue as to what's inside and outside. So we have a reflection. And since it is on the inside, that means it reflects horizontally. So this is a reflection on the y-axis. Then we have this 1/3. That is a dilation. Now remember, it's on the inside, so you have to apply the opposite. And the opposite of dividing by 3 would be to multiply 3. And when you multiply, it gets bigger. So this is a horizontal, because it's on the inside, stretch because we're multiplying, and we're multiplying by 3. Then this minus 3 indicates that we're moving to the right 3, and the plus 1 means that we are going up 1. So now it's time to write our rule. So this represents my parent function, the xy, and now we're going to apply the transformation rule that would give me g of x. Remember that anything on the inside, you must do the opposite except for the negative. You'll always keep a negative if it's on the inside or outside, does not matter. So my rule for the x's will start with negative. Instead of 1/3, it'll be 3, then x plus 3. So everything on the inside, notice that I just did the opposite operation. Negative 3x plus 3. Then the rule for the y, if it helps, just think of everything in pink as being the y and then read it from left to right. So this would be y plus 1. We will always use the same reference points because we are transforming the same parent graph. So we're using negative 1, 1, 0, 0, and 1, 1. And now we plug in those points into the rule. So first I'm going to plug in negative 1. So negative 3 times negative 1 is a positive 3. Plus 3 is 6. Then I plug in 1 into the y. 1 plus 1 is 2. Now I plug in 0, 0. Negative 3 times 0 is 0. Plus 3 is 3. Then 0 plus 1 is 1. And our last point, when you plug in 1, 1, negative 3 times 1 is negative 3. Plus 3 is 0. And then 1 plus 1, which is 2. So these are my 3 points. And now I'm going to go ahead and plug them in. So we have 6, 2. 3, 1, and 0, 2. And you'll see that this is a very wide parabola, and that's because we had a horizontal stretch. And this would be our graph. Additionally, we can see that it did go to the right 3 and up 1. Now the reflection on the y-axis, it does not look any different. And that is because if I go back to the beginning, I'm going back to the parent function. Notice that your parent function is an even function. And it's even because it is symmetric along the y-axis. So if you do a reflection along the y-axis, it's not going to change the orientation of our graph. Let's try one more example. So I'm going to go ahead and highlight everything that is on the inside and everything that is on the outside. So that way I can see exactly what is affecting the x's and what is affecting the y's. So we have this negative. The negative is on the outside, and that is a reflection along the x-axis. Then I have the 2 on the outside, meaning that all of my y values will get multiplied by 2. So that is a vertical stretch of 2. Then I have this 1/2, and it's on the inside, so I have to do the opposite. Instead of dividing 2, my x's will be multiplied by 2. So this is a horizontal stretch of 2. And our last transformations, this -4 means the graph will move to the right 4, and the +3 means the graph will move up 3. So now it's time to write our transformation rules. We have xy, this will be for my parent function. Don't forget our reference points, which are always the same, -1, 1, 0, 0, and 1, 1. So now that I'm ready to write the rule for the x's, remember anything that is on the inside, we are going to do the opposite. So instead of half, instead of dividing 2, we're going to multiply 2, x plus 4. So that is my rule for the x's. And for the y's, remember that this would represent the y. And if you just read it straight across, we have negative 2, which is being multiplied to the y, plus 3. So again, if you just remember anything that is on the inside, think of that as y. So I'm doing negative 2y plus 3. So now I'm ready to plug in my points. When I plug in negative 1 for the x, I get 2 times negative 1, which is negative 2, plus 4 gives me 2. And 1 for the y, negative 2 times 1 is negative 2, plus 3 is 1. When I plug in 0, 0, I get 2 times 0, which is 0, plus 4 is 4, and negative 2 times 0 is 0, plus 3 is 3. And finally, our last point, when I plug in the 1, I get 2 times 1, which is 2, plus 4 is 6, and the 1 for the y, which also gives me 1. So now I can plot these points. So we have 2, 1, 4, 3, and finally 6, 1. And we can see here that not only did we have a vertical dilation, or a vertical stretch, but also that horizontal stretch. We can see that the points are facing down, so my parabola is going to be upside down. And that's because of the reflection over the x-axis. And then it also moved to the right 4 and up 3. So these transformations, again, confirm our work and our graph. Now we're ready to work backwards. So instead of trying to graph a function, we are going to be given the graph and we have to come up with the equation. Now the general form for a quadratic, a transformed quadratic, is g of x is equal to a times x minus h squared plus k. Now a represents any dilations and or reflections that may be present on your graph. And the good thing about quadratics is that any kind of horizontal or vertical dilation, we can just state as a vertical dilation. And that's because a horizontal stretch is the equivalent to a vertical shrink, or a horizontal shrink is the equivalent to a vertical stretch. So we can just do it like that. We don't have to complicate our lives trying to figure out what the horizontal dilation is. Then this h and the k would represent the translations. This is how it moved left or right, and this is how it moved up and down. And you'll notice that in the parentheses, it says minus. And that's because since we're always doing the opposite, if it moved right 2, we would write in the equation x minus 2. So this particular problem, now these are word problems, but the actual wording is just to give you a context of where you would find this parabola. So this one reads, an old stone bridge over a river uses a parabolic arch for support. The vertex of the arch is in point C. Find a quadratic function that models the arch and state the function's domain in interval notation. So we're also going to bring back old material, right? We're trying to figure out what the domain is, which we did at the beginning of the year. And that's because in math, you can't forget things. They always come back up. Math is the subject that everything kind of rolls over from previous years and previous lessons. Everything is related. So I'm always going to try to bring back old material so that way we never forget. Now, when you're working out these problems, I did include some steps for you, just in case if you're unsure of how to approach it, you can always refer back to this slide and follow your steps. So the first step is to identify the vertex of the function. The vertex reveals the translations, how it moved, and that's because since the vertex of your parent function is at 0, 0, if your vertex is located somewhere else, that's how it moved left, right, and up and down. So the actual written description does tell you where the vertex is located, which is at C. But even if it didn't, you would look at your graph and look for that point in the middle. Okay, which is either your maximum, your minimum. In this case, it is a maximum. So the h here would be the 27, and the k would be the -5. So that's step 1. The next step would be to write the function with hk substituted. And then what's going to happen is we're going to have to solve for a. So I like to write out my function. So far what we have is g of x is equal to a, because I haven't found that out yet, x minus the h, which is 27, squared, because remember this is the quadratic, so we do have to include that exponent, and then plus k, which since k is -5, we're going to put -5. So this is the equation of my quadratic. The only thing I'm missing from this equation is to figure out a. So that's what we're going to do now. And how you figure out a is you have to pick another point that's given on the graph. It does not matter which one you choose. You can choose a, you can choose b. You're going to get the same value of a no matter which one you choose. So I'm going to choose a. And what we do is we're going to take this x and y value and we're going to plug it into g of x. Keep in mind that g of x in function notation represents the y. So what I'm going to do is replace g of x with the y value, which is -20, is equal to a times, and then the x value, which is 2, minus 27 squared minus 5. So keep in mind also your order of operations, right? PEMDAS. So we're going to start off with the parentheses. We're going to do -20 is equal to a. 2 minus 27 is -25 squared minus 5. Now I go on to my exponents. So I'm going to apply that exponent. Keep in mind when you apply an exponent, especially squared, that means that it's whatever you're applying the exponent to times itself that many times. This is -25 squared, so that means I'm going to multiply -25 times -25, which gives you a positive 625. And then you have a. Remember, we always write the coefficient before the variable. So 625a minus 5. And we use this to solve for a. So we're going to keep going. We're going to add the 5 over to the other side. And this leaves me with -15 is equal to 625a. And then to solve for a, we just need to divide by 625. So we get here that a is equal to -15 over 625. Once you have your fraction, you can leave it like that. Okay, you don't have to turn it into a decimal or anything. And then we can simplify the fraction. Now, if you look at 15 and 625, both 15 and 625 can be divisible by 5. So I'm going to divide 5 from both the numerator and the denominator. And that would give me a value of a, which is -3 over 125. So this is the value of a, -3 over 125. So now that I have a, I can rewrite my function, but I'm going to plug in a. So g of x is equal to -3 over 125, parentheses x minus 27 squared minus 5. And that's the equation that represents this parabola. And you can look at it and make sure that it matches the transformations that you see on that parabola. We have a negative on the outside, meaning it is a reflection across the x-axis, which is why it's upside down. 3 over 125 would be a fraction, so that's division. This would be a vertical shrink, okay? And you can see that it's kind of like flatter. And then it moved to the right 25, so that's why the h is positive. And it went down 5, meaning my k would be negative. So this is perfect. Now for domain in interval notation. Remember that the domain is all of the x's represented in your function, meaning you want to look for the smallest x to the largest x. So my domain is going to be 2 to 52. And because both of these circles here are filled in, this would be brackets on either side. So the domain is 2 to 52 included. Let's do one more example. This one reads, the netting of an empty hammock hangs between its supports along a curve that can be modeled by a parabola. The vertex of the curve is at point C. Find a quadratic function that models the hammock's netting and state the function's domain using set notation. So here we go. First, we identify our vertex, which is at C. So that gives me H and K. And now I'm going to go ahead and plug it into my general form here. So g of x is going to equal to a times x minus 3 squared plus 3. So I've plugged in my h and k. So I like to just leave that, and I'm changing colors here so I remember this. I'm going to come back here once I figure out a and plug in a. So now you pick another point. Does not matter which one you choose. I'm going to choose B. And I'm going to plug in 8 for the x and 4 for the y, which is the equivalent of g of x. So instead of g of x, I'm going to write 4 is equal to a times x minus 3, so 8 minus 3 squared plus 3. So we have 4 is equal to a. 8 minus 3 is 5 squared plus 3. Apply the exponent. 5 squared is 25. A plus 3. Subtract the 3. We get 1 is equal to 25a. And finally, divide the 25. And we get that a is equal to 1 over 25. So now to write out our equation. Remember, you're going back to the original and you're not changing anything except you're substituting a with what you found. So g of x is equal to 1 over 25 times x minus 3 squared plus 3. And this is the equation that would represent this parabola. Now to write the domain using set notation. Remember, set notation is the one that opens with the brace. Domain represents our x's. My smallest x is negative 2, less than or equal to, because it is a filled circle, x in the middle, less than or equal to, and then my largest x, which is 8. And that would be your domain for this particular function. And that's transforming quadratics.